Been telling you about the VRs, right? So, what is a VR? VR is a place where the wire changes layer. This is a VR. So, metal has to be deposited here properly for the connection to occur. And if the VR does not have a proper contact, okay, because not enough metal was able to get in, right? Then the contact will be either improper or it may be completely missing altogether. If it is missing altogether, if VI is missing altogether, then of course this becomes a open fault. Okay. So for example, maybe there is a gate and it goes to another gate, and this wire was crossing two different layers, and there was no VR properly. So as a result, it appears to be stuck at. It appears to be open here, and an open here may possibly look at a. It may look like a stuck at one fault. So there is a stuck at one here and a stuck at one here. An open can be modeled as a stuck at 1 or a stuck at 0 depending on the logic family. See, in TTL logic family, if a input is open, then it behaves like a stuck at 1. In CMOS, it will behave like a stuck at 0, right? But unfortunately, what could happen is this wire is not entirely missing, okay? But it is providing a high resistance. Okay, there is a high resistance between the two. It's not an open, but high resistance. An open is a perfect, like a infinite resistance. But a VR which is not properly formed may present a high resistance. So in that case, how does the circuit behave? Okay. It will not have a functional fault. See, the stuck at fault, which causes an output to become 0 or a 1, that will not happen here. Okay. The connection is still there. What will happen instead is the speed performance will be affected. Okay. So remember, if I have a wire, that wire will have some resistance and some capacitance. Okay. If this wire is being driven by some gate, and let us say the output changes from 0 to 1, at the other end, because of the resistance and the capacitance, there may be some delay. The output will go from 0 to 1 with some delay. But if this resistance is very high, okay, then this output will go from 0 to 1 much slowly. It may go like this. What is the delay? The definition of transition delay is the time it takes for the output to reach 90% of its value, starting from 10% of its value. So this is the delay when there is no fault. That means when the VI is good. But this is the delay when the VI is bad. So the delay got increased. So the VIA which is badly formed results in a higher delay. And it is possible that a circuit goes through a number of vias, right? I mean, I'm sorry, a wire goes through a number of vias. So they will all add up. Okay, imagine that there is a wire which is going through a number of vias, and there is a small chance that everywhere that via problem is there. Okay, each of them is adding a little extra delay. So overall, the delay can be very bad. So when we design circuits, so in sequential circuits, remember how it works. So there is a primary input, there is a primary output, there is a next state, and then there is a previous state. And there may be flip-flops. There may be many primary inputs and there may be many primary outputs. And there may be many, I mean, I have only shown two, but there could be many. The clock is supposed to synchronize these guys. The clock is supposed to synchronize these two guys. So when, let us say, the clock comes, usually the circuits respond to the positive edge of the clock. Okay, these positive edges. So let us say this guy got, both of them got a positive edge, and let us say this is my D input. So when the positive edge comes, this D input will have to get transferred to this Q. Okay, so there is some delay which is called the delay from D to Q. Okay, it takes a little small amount of time for the D to get transferred to Q, and that change may propagate along some path. Maybe there are wires, maybe there are gates. Okay, let me draw it properly. Maybe there is a wire, then gate, wire, gate, okay. And ultimately it will, let us say, come to this guy. So this is called as a launch edge. So D1 was copied to Q1 here, somewhere here. And then it is taking some time for the output to change, okay, because there are so many wires, right? I explained to you that each wire will have some delay, and some of them may be higher than expected because of via problems and so on, right? See, we would have adjusted during timing analysis, we would have calculated the path delay, okay, and we would have made sure that all paths are done before the next clock comes. So this is known as a capture edge. So when the transition is launched from D1 to Q1, there is some delay along this path before it gets ready for D2 to get captured in the capture edge. So this is, we would have adjusted the total clock period. Okay. So let us say this clock period is T. We would have made sure that T is greater than the time it takes for this D to Q plus path delay plus this so called setup delay. I think a better way to write it is clock to Q. It takes some time for this clock to launch it to this Q. Okay. So there is a clock to Q delay at D1 plus there is some path delay, right, plus some setup time. Okay. So we though the period is T, this time is to be taken away and this time has to be taken away. Now if the path delay, let us say, is higher than what we anticipated, then there could be a problem that this equation is no more satisfied, this inequality is no more satisfied. If the path delay is higher, right, then there will be a failure in the sense that a wrong value will get captured. The old value of on this wire will get captured here. The new value is not get captured. This D was supposed to have been captured into Q1. It has to travel and then the new value must get captured here. But unfortunately, the circuit was not ready by the time the launch edge came, and as a result, the old value get. So old value may get um, old captured in Q2. So that results in a functional failure. Okay, the circuit will go into a wrong state. It should have gone to a different state, okay, but it entered an incorrect state. So maybe initially the circuit was in the 0 0 state and it should have gone to the 0 1 state, but it remained in the 0 0 state. So that resulted in a faulty behavior. See, unfortunately, stuck-at faults will not be able to detect these kind of things, right? Because remember what we do in stuck-at faults, we just look at the combinational part, right? And we generate test patterns for the stuck-at faults in the combinational logic, and then we use the scan chain. We convert this all the flops into a scan chain. That is how it works. So at that point, we were not even looking at these kind of problems. We have not looked at timing failures. So this is actually a timing driven caused by timing. The functional failure caused by timing. It is not a failure of the logic. It's not that an AND gate has a stuck at one fault at the output. No. If you slow it down, if you are willing to slow down the circuit, okay, maybe you had intended this circuit to work at 100 megahertz. Okay, so the frequency was expected to be 100 megahertz. If you are willing to make it work at, let us say, 10% lower, it may actually work correctly because now this inequality is satisfied. Okay. But if you try to make it work at 100 megahertz, the circuit doesn't work. Okay, so this is only the speed related fault. Okay, it has nothing to do with stuck at behavior or any functional fault. It's not a functional problem. There is nothing wrong with the circuit. It's designed correctly. It is, it doesn't have any stuck at fault in it, but it has more of a speed related fault.